Okay, hopefully everyone can see my screen okay. I'd like to change to the laser pointer as well. Okay, so thank you everyone for attending my talk. I'm going to be talking about a paper that I did together with Luke Dickens, Artur, Garcez, and Alessandra Russo. They're all my supervisors, and it covers 3 universities in London: Imperial College London, UCL, and City. The paper is Coherent and Consistent Relational Transfer Learning with Autoencoders. So let's just jump right in. So human-defined concepts are inherently transferable. Once we learn the concept, whatever that would be, we seem to be able to reuse it in many different situations, but it's not very clear under what conditions we can say the same thing about non-symbolic learners, such as neural network-based methods. In this paper, we propose that concept coherence is key to this transferability, and hopefully by the end of this presentation, you're going to agree with me. So going a little bit deeper, when you learn a concept successfully, it means it should be consistent. So for instance, if you're learning the concept of ordinality, which allows you to compare objects in terms of some sort of magnitudal type property, so like A is greater than B or A is equal to B, you should know that after learning this concept successfully, that A cannot both be greater than B and equal to B. This is an example of being consistent. A coherent concept retains its consistency regardless of context. So essentially what we have is a sort of context invariant consistency. It doesn't mean that ordinality means one thing for one data set and one problem, and it's totally unrelated in a new domain of interest. So as examples of sort of domains we look at, or contexts, I refer to a context, by the way, as a domain together with a task. So if you change the task, we're kind of changing the context. So let's say we have a domain such as MNIST containing images of handwritten digits, and the task is to simply put them in order. In a separate setup, you might have another domain, which is the one we present in our paper, which is a domain of images of stacks of blocks. The blocks can be multicolored, but critically, each one has one single red block inside it. And the task in this case would be to compare the block stacks in their red block height, which is a little bit more tricky than comparing them in the overall block stack height, because, for example, that was very lag. This block stack is higher than this one, but yet the red block in it is lower. So in fact, you put this one after this one. So if you did this with no prior knowledge, in the initial case, you have to learn the concept of ordinality, saying things like 5 is greater than 3. Underneath ordinality, there would be relations such as this: is greater, is less, is equal, is successor, is predecessor. And then in the target context, you would hope to reapply this concept. And with no learning, you'll be reliant on having the consistency that you obtained of ordinality in the source domain should be what allows this to be possible. And we refer to that as this coherence, this context invariant consistency. This brings me to the experimental setup we use in the paper. So we have 2 principal phases in the overall experiment. We have a relation learning phase, RLP, where we learn a set of relation decoders. So a relation decoder is essentially a function that models a relationship. And you learn this in a source domain and task, source context. In the transfer learning phase, the second step, we apply a subset of the relations to a different but related target domain and task, but we fix the parameters of the relation. We do no relation learning. In both domains, we use domain-specific autoencoders to obtain image representations for the relation decoders to operate on. And I'll go into more detail about that when I get to the full architecture. But I'm saying here that we're using some relations in the second phase. Even though we want to essentially just test if the relations still apply, we do actually use some of them, and I say a subset, and I'll hopefully explain why we have to do that. So there are a few intricacies when you're doing this kind of learning problem, where you have 2 different data sets, and you're trying to compare in each data set a different property. Data sets vary in the dimensionality, in their size, and color aspects. So, and this is grayscale, block stacks is RGB. And so we necessitated to use a new encoder, but there's no guarantee you get a useful target encoder. So the encoding of your target data set, you can't be sure that it's going to play nicely with these relation decoders you learned together with a different encoder. So I have some more slides at the end if I have time to get to. I'm not sure if I will, but the main takeaway for for now would be that the target encoder needs some sort of guide to ensure that it does a sort of common encoding that plays nicely with the relation decoders. I also say that we use only a subset of relations. So why is that? You could use all of them to do this kind of alignment or guiding of the target encoding. But if you did a successful acquisition of a concept, ordinality in this case, you should guarantee that the underlying rules hold. So you shouldn't need to include redundant relations. In fact, in our work, we only use the is-successor relation. So you kind of have this flow where you're going to be learning target-specific or domain-specific encoding to get this representation, but it's going to be optimizing against improving the is-successor relation accuracy, but without changing the is-successor relation parameters. We can understand this better if I look at the architecture now. So, more in depth, our architecture actually consists of domain-specific beta VAEs, variational autoencoders. We use a beta and coupled with domain-independent relation decoders. So the reason why we use a beta VAE is because it's got a beautiful little beta parameter which encourages the representation, the intermediary representation, the data encoding to be factorized. And it's argued that this simplifies the representation. Factorized means that the details of the input domain, in this case the images, should be separated into independent components with the intermediary representation, this red one here. And we also include here you'll notice that we don't just have an encoder, we have a decoder that reconstructs the image. The reason why we do that is because we thought it'd be more interesting to try and obtain a feature complete representation or an information complete representation of the image. So you don't want to just ignore everything and just have a representation for some ordinal property. You want it to capture other details too, alongside that ordinal property. When we move to the target domain, what we end up doing is switching out the autoencoder, but leaving everything else in terms of parameters. So we have a new initial set of autoencoders to learn. But because the relation decoders are modular, we can remove some of them. They're kind of like extra sort of output or decoder heads to the overall architecture. So what you can have here is that the set of relations in the target domain is a subset of the set of relations in the source domain. In this case, we only then have the is-successor relation decoder present during training of the target autoencoder. So when we're fixing the parameters of the relation decoder, what essentially happens is the only way that the target-specific encoder can optimize against the is-successor relation, improving this relation decoder loss we have here, which forms part of the joint loss that we train against, is if it changes the encoding. So this is how it does that kind of guiding aspect. So in our work, we actually present our own version of a relation decoder called dynamic comparator. And rather than staying here on the math, because I think I'm not speaking for a very long time about it, I think it's more useful to kind of see visually how it works. So the blue line here models the is-greater relation, green is the is-successor relation, and red is the equals relation. The x-axis is supposed to give the difference between the 0th component of a representation for an image instance I and an image instance J. Now, when I is greater than J, saying that when some property about image I is considered greater, the ordinal property then, is considered greater than that same property in image J, you would want that the difference, and let's say this is encoded in the 0th component of the vectors, you would want that if this difference is positive, is greater is positive, which is what you get here. And we consider a value close to 1 as being true and a value close to 0 as being false. Now at 0, you don't want is greater to be true, you want is equals to be true. So you see how as is greater drops off, is greater pops up. And if there is successor, you have this setup where you want the difference to be a unit bigger. Say the unit was 1, then you want to have this kind of thing here where at the difference of 1, is successor is true, is greater will then be true too, but is equal to be false. So even though we actually have a very simple function, it's able to select different shapes to model different kinds of relations. And through offsets, it can actually express these relations compatibly with each other. We have some other models that we test against. For example, these are trans R, whole E, and NTN. These are coming from the literature. And we also have, but they're actually, trans R and NTN, I should note, are slightly modified. This is so that they model Boolean type relations. So their values are kind of constrained between 0 and 1. But we also include a neural network that we put together just to see how it would perform, which contains 2 hidden layers and sort of forms a bit of a funnel where it goes from 2 times the dimensionality of the latent space down to 1 times, and then down to a single value output, which has a sigmoid wrapped around it to make sure it also is outputs between 0 and 1. Cool, so now we can get to results. I think I made good time so we can talk about them enough. So first things to look at was the overall accuracy and performance of each relation decoder in the source and target domain, just to understand if they're actually doing, they're learning the task properly, the initial ordinal task. The left side tells us that they did manage to learn some notion of ordinality, or at least get a good accuracy on predicting ordinal relations. So, and on the right-hand side, you'll note that this S is successor, so the abbreviations are up here. S is colored red and is sort of separated from the others, and this is because we are optimizing against it. We're not learning it in the target setting in the transfer learning phase, but we are optimizing against it. So you have to consider it a bit differently to the others. But these relation decoders here, is predecessor, is equal, is greater, and is less. These ones can only have a boost in performance if the alignment of the target encoder to optimize against its successor transfers, some element of that performance transfers to the other relations, which we kind of expect to happen in a symbolic sense, because you could express these other relations in terms of the successor. Interestingly, so first off, most models do pretty well, close to about 0.9 minimum accuracy on all relations on the MNIST dataset, the source domain. But not all, their results vary a lot, especially on the held out relations in the target domain. DC, first off, seems to do very well. It obtains close to 100%, or if not 100% accuracy across all relations, whether they are the ones they optimize against or held out. Neural network performs surprisingly well. It has its greatest degradation. We say surprisingly well because we weren't actually expecting that. We thought there was going to be such a high capacity model compared to the others that it would sort of learn the task in a very domain specific way and wouldn't have this coherence of the ordinal concept. But we do find that it does quite well. Note that here, we were changing the beta value of the source encoder. So this is selecting the best beta value for each relation decoder to give these results. And you'll see in the next slide how that affected their results. And an interesting property in this regard for neural network is that, and others actually, is that they seem to suffer on the is equals relation. But neural network specifically, you can see how it does good in most of them, but then on is equals, it seems to do a bit worse. Is equals is a funny one because in terms of MNIST, comparing if 2 numbers are equal, you're really comparing if 2 shapes are the same. And that's quite interesting because the numeric attribute associated with a number, essentially, is quite non-visual. So what I think is happening here, and the beta value seems to support, is that the neural network in the source domain might be using other sort of stylistic or visual properties to do its is equals encoding. So it's quite an interesting thing going on there. Other models that, interestingly also, Transar, which is actually a relatively low capacity model, seems to do a very good relative performance relative to its source domain accuracies. And we see Holy and NTN having a steep drop off as we get to greater and less than. So there might be some, but the thing is they can model greater and less than in the source domain. So it's interesting to see why that might be. It's likely that the way that they model greater and less than is sort of different, I'll say, to the way successor is modeled. And this is in terms of the region of the aspects of the data encoding that they might use to produce their prediction. So now we look at the beta values. I should probably move faster. So the darker shades show the increasingly higher values of beta that we applied in the source domain learning phase, in the relation learning phase. We can see that DC is not influenced by changes in beta, and that's because we kind of baked into DC this notion of the same thing that beta tries to do. DC kind of already is biased towards. We often see a negative influence of beta in the source domain, but in the target domain, we see something quite different. And it seems that if you set the value around a medium range, you get a boost in many cases. Neural network is very interesting because you get a specific boost at beta equals 8. Otherwise, it does comparatively worse. Trans R seems to continue to do better as betas increase. So there's a lot going on here. But I think what happens here with NN, neural network, is that this is where it starts to disambiguate how it's computing the is equals relation with respect to the other relations having to compute. So now we're going to look at some intrinsic results, sort of looking under the hood of how this accuracy profile occurs, how beta is effectively changing the way that the different models perform. In doing so,
Harry, we need to hurry up a little bit. Thank you.
How long do I have? How long do I have?
No. Try to conclude in the next few minutes. Thank you, Harry. Sorry about that.
Getting there. So we have three different data splits that we report our results on. Data embeddings, which are exact encodings of test data set of each data set, data instances of each data set. Interpolation, which looks around one standard deviation from the empirical mean of the data encoding distribution, assumed to be a simple Gaussian. And then we have an extrapolation region, which is looking outside of all of the encodings. So the consistency across evaluates the binary cross entropy of relational decoder outputs against expected rule truth states. So we know that, for example, is greater Zi Zj should imply that not is equal Zi Zj. That should always be true. And we can do a sort of approximate calculation for what the relation decoders think about that rule. Lower values are better. And the main takeaway is that DC retains higher consistency across different data splits than the other models. And this seems to correlate with a better performance in the target domain consistency on target domain data embeddings. Yeah, and beta seems to improve this value. It brings where we again see around a medium value, models are doing the best in their target domain data embedding consistency scores. I can move on from here. And this, if you compare the blue on the left and the blue on the right, which are the data embeddings of the source domain and the data embeddings of the target domain, their relative consistency, this is sort of indicative of the coherence. The takeaway here is that the ability to retain consistency on the interpolated or extrapolated regions helps coherence, and this correlates to better partial relation accuracy, where you can see that the models which have a lower target blue consistency generally seem to be doing better. We have some new results that further support this. Okay, so since I have to hurry up, I'll verbally.
Yes, please conclude. Sorry about that. Okay,
sorry. We also looked at how the gradient fields align of the various models when you compare and on different data splits. And generally, we find that more gradient alignment of how their output changes with respect to changes in the input space seems to also support the fact that they are more coherent. And this might be how beta is actually affecting models and improving their results. So in conclusion, relation decoder's ability to retain consistency over arbitrary regions of represented digital space improves consistency in the target domain. And a suitable beta regularization seems to help encourage this aspect, potentially via a GC increase. There's some future work here, but I think I can conclude already, so I'm happy to stop here. Thank you very much for your attention.